And now let's go ahead and work tasks 3 and 4 for our stopwatch lab. We want to change our HLSM so that now we have a maximum value that the stopwatch can count to. So we're going to use the values of the switches 7 through 0, to set a maximum value. The first thing we have to do is to create a new HLSM. And basically it looks exactly the same as our last HLSM. Let me scroll down through a couple of these and get to our additional behaviors for task 3. And so we see that basically when we are in the run state, it will continue to count until either we press S, or if the maximum value gets to the maximum value set by the switches. Okay, and so it's counting here, it's counting here, it's counting here, and if the value T is equal to the value of M, which is the value of the switches, the stopwatch will stop and it will transition back to the stop, which is actually where it stops. Okay, and so our HLSM is almost exactly the same here, except that we have an arrow coming off of S run that says check to see if T is equal to M. Okay, and so we can think about that, and really we're not going to add any extra states. We just have to add an additional component to our data path, right? And so notice here that our stopwatch output looks almost identical to the one from tasks 1 and 2, except now we have a new input, M, which is the value of the switches. Okay, and so for task 3, we're going to add basically this maximum value, okay? And we're going to do that by adding a comparator. We have to compare the value of T to the value of M. Notice that we have this additional input, 8-bit input M, okay, which is the maximum time. And so we're going to check every time we count to see if T is indeed less than M. If so, keep counting. If it's not less than, then we transition back to stop. Okay? In order to do that, we notice here that the only difference for when we're looking at the black box, our top level, that M is an input that gives the maximum time. Okay? Continuing down, sorry, I sort of have to do it this way. That now, looking at our new HLSM, that all we have to do is add the new input M, which is again 8 bits wide. Everything else looks exactly the same. Okay, and so we have that. Now notice here that our transitions are different, right? Here's our transitions. We have that originally it was S0 R0. Now it's going to be S0 R0, or this combination of S R0 and with the fact that T is not, that T less than M is 0. If so, then we stay in stop. If not, then we come over here to S run. Notice here, if T is indeed less than 0, we add that to our transitions, and so we have that on our transition state, our transition wire, and so that takes us into the S run state. Okay. All right. And so we have that, and we can go ahead and just look at a few other things, because notice we have to change this as well, okay? If S is equal to 1, and also checking, or that S is equal to 0, and T is T less than M is false, okay? And so we'll talk about how we can do that. Notice we're back to our processor architecture. What is it that we need to change? We're changing this data path, right? We're changing the data path. Our data path was just a counter. Now we want to have our data path to include a counter and a comparator. Let me go ahead and stop this. And okay. And so what I have done is I have actually created a whole new project. I've called this Stopwatch Revised. It is your choice whether you want to create a whole new project. And then after I created this new project, I just moved all of my files. I copied all of my files from my original Stopwatch project to my new project. Again, make sure that they are all in the local directory. I don't want to see any subdirectories in your list of files that are added to your project. Okay, it will not work, and I don't want to come and debug it. So you better have it so that everything is in the local directory, just like we have it listed here. No subdirectories, no paths that have a slash before the name. All right, and so once you've done that, you've created this new project called Stopwatch Revised. We're going to basically do exactly the same thing that we did before, except we're going to start again with our data path. Notice I have my LPM counter just like I did before. Didn't make any changes to it. I now have added an LPM compare. I want to use a comparator to check whether or not T, the output of the counter, is equal to or less than the output of M. I have M coming in as my data B, and I have T coming in as my data A. Finding this symbol, you just again come here and come to the libraries, come to the mega functions, come to the arithmetic, and just scroll down until you find the LPM compare. And so there's our LPM compare. You can just add that just like I've done here. I grounded my asynchronous clear. We would expect that. And I've also set my clock enable equal to VCC. I did not use my clock for this particular symbol. I let it just be a combinational logic. This is probably left over from a previous lab that I was doing. Go ahead and just set clock enable. I don't have my clock tied to anything, so I'm not using it. So you probably don't need that clock enable. Your choice. Okay, I had to set the parameters. The parameters, I want my LPM width equal to 8, and I have a chain size equal to 1, which basically means that I have one flip-flop in there. Okay, so your choice. You can go ahead and use the clock or not. If you use the clock, I think you may end up with a little bit of counting errors, so I would skip using the clock. All right, so that is the second symbol we need in our data path. We know that our processor design, our processor architecture has our data path components, and then we have a controller that's going to control the inputs, these lines that are coming in. We create a symbol, and we and go and add it to our symbol. Make sure you update it. Notice here I have some new inputs. I have M coming in, and I have less than going out. Okay, this is the output of the comparator, and then I have also this data path also has the counter in here. I have the values of T. Okay, I have some new lines coming out of my FSM. Okay, I have to handle clear and increment based on what the values that were going into the data path. Notice less than is coming out of the data path, going into the FSM. We know that the FSM is made up of our state register and our combinational block. Okay, we know that when we come back and take a look at our controller design, that basically we've made some changes. We've added these additional changes that you have to change your state table to handle those. I'm sorry, we have to handle all of them, so we have to handle these as well. Make sure that you take that into account when you come up with your new equations for your new combinational logic circuit. And then you also, there were some students that were concerned about the differences between the FSM and the HLSM. Know that this is an assignment statement for a multi-bit output. This is an assignment statement for a multi-bit output. We have that colon equals to. When we create the FSM, we change these to what we need. This becomes clear equals 1. This becomes increment equals 1. Those are the outputs out of our combinational block, out of our FSM, that is then fed into our data path, right? The control lines out of our FSM are the inputs, the control inputs into our data path, clear and increment. Okay, this is the difference between designing just an FSM and designing a processor, right? Not just a controller. Now we have an entire processor that we're designing. Okay, so that should take you through. Those are basically the only changes you need to make. Make your changes in your combinational logic. Your state register looks exactly the same, right? And so no changes there. And so just change in combinational logic your equations. Then once you've run your tests, again, you're running your tests on the stopwatch.bdf. Okay, You're running, this is a new stopwatch test for the revised project. So make sure that this is your top level. If it has a different name, right? And you have your assignment statements. Your assignment statements should all be set. We have the simulation. You should have your run gate level simulation set. You should set this to compile test bench. Set up that it's going to call your stopwatch underscore test.vt. Accept that and set up a script. You want your do file in here. And so you have your do file. Make sure that you have those if you're running model sim, right, for the stopwatch level of our project. That's where we want to run model sim. So if you're at this level, go ahead and set those settings. Run model sim. Make sure that it runs such that you get all tests passed. And then once you do that, go back to assignments, change the settings, go back, take off your run gate level simulation, set your native link settings to none, right? Bring up the top level. You've created a symbol for your stopwatch. Add that symbol here. Update this symbol, right? Because you're going to have a different symbol, one that you've created. Here is our clock divider. Again, we've divided down so that we can run at a much slower speed. Notice again, I have 24 bits here. This is all given to you, a 24-bit clock divider. And so then I am using the clock divide 18 to handle this input. So, whoops, didn't mean to do that. And so here I have my bit that I'm using. Okay, you may find that you want to use a slower bit. You can always change this. You can slow it down some by using any of these bits. I chose clock divide 18. You could use 19, 20, 21, 22 to keep slowing it down. That will slow it down a lot. Okay, I have my additional circuitries. This makes sure that you hold it for at least 15 counts. This is about a 4-bit counter, so you have to hold clock down, or you have to hold S down or R down for at least 15 counts to make, that's when it recognizes it. And then I have an extra flip-flop just to slow it down a little bit more, and I have a one-shot so that I just have a single rising edge on that S or on that R so I don't get glitches. Okay, my outputs, switches 7 through 0 are the values where M is, and I'm still using key 3 for S and key 2 for R. I have key 1 for my reset. Okay, this is the overall reset, that asynchronous reset for those flip-flops of the states. We'll take it back to state 0. Okay, I hope that helps. Take care. Bye.